Okay, so today we are going to start by talking about the equilibrium constant for water. So what we're going to look at is what happens whenever we hydrate a proton, or in this case it's called the hydronium ion. So the first thing we want to do is consider the Arrhenius reaction. So that's whenever we have an acid that dissociates into H plus and A minus. So that was the Arrhenius definition. And then we also looked at the Bronsted-Lowry definition whenever we looked at proton acceptors and donors. So the only real difference was whenever we looked at Bronsted-Lowry acids and bases, we might have something like this for an acid. We had Ha plus H2O yielding, and then our products would be hydronium, H3O plus, and then also our conjugate base right here. So the only difference is, in the Arrhenius definition we had H plus, in the Bronsted-Lowry definition we have H3O plus. So what I'm going to try to show you today is that this actually means the same thing for us. Because what we'll end up seeing is if we have H plus, so that proton in solution, it will interact with the solvent, which will be water, and it's going to actually end up forming the hydronium ion, so H3O plus. So even though you'll see it written as H3O plus or H plus, it means the exact same thing. So now let's go ahead and start to consider water. As we've looked at water previously, we've seen that it can act as either an acid or a base. It depends on what else is present. So if an acid is present, water is going to act as a base. If a base is present, then the water will act as an acid. So let's go ahead and look how water behaves by itself. So water will actually dissociate to form the hydronium ion and the hydroxide ion. And sometimes you'll see this chemical reaction rewritten in a simplified form here. But if we were to write out an equilibrium constant for this, we'll call this Kw, where K stands for the equilibrium constant, and then W specifies that it's for water. Kw is going to be equal to the concentration of H3O plus times OH minus. And then what we'll end up seeing is at 298 K, which is the temperature that all of our reactions will be carried out for in this class, Kw is a constant. Kw is equal to 1.0 times 10 to the negative 14th. So again, this is just like any other equilibrium constant. Just here, the W specifies that it's for the dissociation of water. So let's go ahead and consider in pure water, at 298 K. So I already told you that Kw is going to be equal to 1.0 times 10 to the negative 14th. And that Kw would be equal to the concentration of H3O plus times OH minus. What we'll see is that for pure water, the concentration of H3O plus will be equal to the concentration of OH minus. So in this case, what we'll usually do is we don't account for water dissociating on its own, okay? Whenever we're looking at different solutions and acids, we never account for the amount of hydronium that's contributed by the water because it's so small. And so what I've done down here is I've shown you a quick calculation to show the actual concentration of pure water versus the concentration of hydronium in a sample of water. And so if we go ahead and use, this is the density of water, which you might sometimes see written as 0.997 grams per milliliter. Well, we could go ahead and change that to how many grams per liter. In converting that to a concentration, you'll see that the concentration of pure water is 55.4 molar, which is a huge number. Think back to whenever we first started with molarity. We were looking at concentrations that were, if they were 1 to 5, we consider that to be a huge number. So 55 is a whole order of magnitude greater. So if we were to compare the concentration of the water that's dissociated, so this hydronium concentration here, versus the concentration of the undissociated water, what we'll see is this ratio is 1.8 times 10 to the negative 9th, which means that about 2 water molecules in 1 billion are actually dissociated. So we don't actually have to worry about the contribution of hydronium ion from water. It depends on what's present, whether an acid is present or a base is present. So let's go ahead and look at this a little bit further. So we can see that Kw again still equal to H3O plus times OH minus. So we've always encountered acidic and basic solutions in previous classes like physical science or biology, but now we actually have a quantitative meaning. And so we're going to keep on working through this and try to figure out what it means to be acidic or what it means for a solution to be basic. So as we go through and we try to answer these questions, what we want to realize is that we're only considering dilute solutions, where water is almost pure liquid, and again, there's not an appreciable concentration of hydronium and hydroxide ions. And that makes things a lot easier in the long run. So now, let's go ahead and see what this looks like in these different types of solutions. So, keep in mind, let's look at an acidic solution first. So let's just look at a general reaction. So here's our general reaction for an acid. So we'd have our acid plus our water. And we know that acids donate protons and bases accept protons. So in this case, we're going to be left with our hydronium ion and then our conjugate base. So what this means is if we have an acidic solution, so water's in the presence of an acid, we're actually going to increase this concentration of hydronium. So the H3O plus concentration will be greater than the OH minus concentration. In a neutral solution, we'll have the same amount, or practically the same amount, of hydronium and hydroxide. And so if we were to consider a base, let's look at a base reaction. So we have our base plus water yields, well, bases accept protons. So we have BH plus OH minus. So we can see for the general reaction for a base that we're going to end up with more hydroxide present than hydronium. So we could write the expression like this. So keep this in mind as we start to look through and compare a concentration of H3O plus to OH minus. If H3O plus is greater than OH minus, it's acidic. If they're approximately equal, or at least on the same order of magnitude, there's a good chance it's neutral. And then if the hydroxide concentration is greater than the hydronium, then it is in fact basic. So let's go ahead and try a sample calculation. All right, so in this problem, we want to calculate the hydroxide concentration from Kw and H3O plus. So what I'll go ahead and tell you is the concentration of H3O plus ions in a sample of lemon juice is 2.5 times 10 to the negative third molar. So this is the H3O plus. If it doesn't tell you that the temperature is 298, we're going to assume it's 298. So if it's 298, what we know is Kw is equal to 1.0 times 10 to the negative 14th. So let's go ahead and we want to go through and calculate the concentration of OH minus and classify the solution as acidic, neutral, or basic. So we can go ahead and say, well, we know that Kw is equal to the hydronium concentration times the hydroxide concentration. So if we're trying to find the hydroxide concentration, we can rearrange this to say that OH minus is equal to Kw over H3O plus concentration. Substituting in, for Kw we'll have 1.0 times 10 to the negative 14th divided by the hydronium concentration that was given, 2.5 times 10 to the negative third molar. We'll plug this in, and the OH minus concentration is 4.0 times 10 to the negative 12th molar. So we know that the hydronium concentration, H3O plus, is much greater than the OH minus concentration. Therefore, our solution is acidic. So make sure as you're going through and working with something like kW, remember that our equilibrium constants do not have units. But if we're solving for a concentration, those units will come back into play for our final answer.